Namaskar, I am Dan Gowde, Assistant Professor in Mathematics, Center for Distance Education, Shivaji University, Kolhapur. Today I will discuss the independence and linear dependence. One more definition. Assume that each of the function f1 of x, f2 of x, dot 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 fn of x are differentiable at least n minus 1 times in the interval ab. Then the determinant f1 of x, f2 of x, f3 of x, dot 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 fn of x, f1 dash of x, f2 dash of x, f3 dash of x, dot dot fn dash of x, f1 double dash of x, f2 double dash of x, dot 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 fn double dash of x, f1 raised to n minus 1 of x, f2 raised to n minus 1 of x, dot 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 fn raised to n minus 1 of x, denoted by w of f1 f2 dot 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 fn of x is called wronskian of the n function f1 f2 dot 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 fn. Next theorem. Two solutions phi1 and phi2 of L of y is equal to 0 are linearly independent on an interval I if and only if w of phi1 of phi1 phi2 of x is not equal to 0 for all x in I. Suppose w of phi1 phi2 of x is not equal to 0 for all x in I. Let c1 c2 be constant such that c1 phi1 of x plus c2 phi2 of x is equal to 0 for all x in I. Then c1 phi1 dash of x plus c2 phi2 dash of x is equal to 0 for all x in I. Above two equations can be written as phi1 of x, phi2 of x, phi1 dash of x, phi2 dash of x, c1 c2 is equal to 0. Since w of phi1 phi2 of x is not equal to 0 for all x in I, the coefficient matrix is invertible. By pre-multiplying the inverse of the coefficient matrix results in c1 is equal to c2 is equal to 0. This proves that phi1 is equal to phi1 and phi2 are linearly independent on I. Conversely, assume that phi1 and phi2 are linearly independent on I. Suppose that there is a point x0 in I such that w of phi1 phi2 of x0 is equal to 0. Then the system of equations w1 of phi1 of x0, phi2 of x0, phi1 dash of x0, phi2 dash of x0, c1 c2 is equal to 0 has a solution c1 c2 where at least one of these numbers is not 0. Let c1 c2 be such solutions and consider the function psi of x is equal to c1 phi1 of x plus c2 phi2 of x. Now L of psi is equal to 0 and psi of x naught is equal to 0, psi dash of x naught is equal to 0. Then norm of psi of x naught is equal to uh, psi of x naught square plus psi dash of x naught square brackets raised to a half is equal to 0. By theorem, norm of psi of x is equal to 0. Therefore, norm of psi of x is equal to modulus of psi of x square plus modulus of psi dash of x square is equal to 0. Therefore, psi of x is equal to 0 for all x in I, and thus c1 pi1 of x plus c2 pi2 of x is equal to 0 for all x in I. But then pi1 and pi2 are linearly independent. Then the function suppositions phi w of pi1 pi2 of x naught is equal to 0 must be false, and therefore w of pi1 pi2 of x is not equal to 0 for all x in I. Next theorem. Let phi1 phi2 be two solutions of L of y is equal to 0 on an interval I. Let x naught be any point in I, then two solutions pi 1 and pi 2 are linearly independent on I if and only if w of pi 1 pi 2 at x naught is not equal to 0. If pi 1 and pi 2 are linearly independent on I, then by theorem w of pi 1 pi 2 of x is not equal to 0 for all x in I. In particular, w of pi 1 pi 2 of x naught is not equal to 0. Conversely, suppose that w of pi 1 pi 2 of x naught is not equal to 0, and suppose c1 c2 are constants such that c1 pi 1 of x plus c2 pi 2 of x is equal to 0 for all x in I, then c1 pi 1 of x naught plus c2 pi 2 of x naught is equal to 0, then and c1 pi 1 dash of x naught plus c2 pi 2 dash of x naught is equal to 0. Pi 1 of x naught, pi 2 of x naught, pi 1 dash of x naught, pi 2 dash of x naught, c1 c2 is equal to 0. But since the determinant of the coefficient is w of pi 1 pi 2 of x naught is not equal to 0, we obtain c1 c is equal to c2 is equal to 0. Thus pi 1 pi 2 are linearly independent on I. In the next theorem, let a pi 1 pi 2 be any two linearly independent solution of L of y is equal to 0 on an interval I. Every solution pi of L of y is equal to 0 can be written uniquely as pi is equal to c1 pi 1 plus c2 pi 2, where c1 c2 are constant. Let let x naught be a point in I. Let pi of x naught is equal to alpha, pi dash of x naught is equal to beta. Since pi 1 and pi 2 are linearly independent on I, we know that w of pi 1 pi 2 of x naught is not equal to 0. Consider the two equations pi 1 of x naught, pi 2 of x naught, pi 1 dash of x naught, pi 2 dash of x naught, c1 c2 is equal to alpha beta. Since w of pi 1 pi 2 of x naught is not equal to 0, the above system of equations has a unique solution c1 c2. For this choice of c1 c2, the functions of x is equal to c1 pi 1 of x plus c2 pi 2 of x satisfies psi of x naught is equal to c1 pi 1 of x naught plus c2 pi 2 of x naught is equal to alpha is equal to pi of x naught. Psi of x naught is equal to pi of x naught. Similarly, psi dash of x naught is equal to pi dash of x naught, and L of psi is equal to 0. From the uniqueness, it follows that psi is equal to psi is equal to pi on I. Therefore, pi is equal to c1 pi 1 plus c2 pi 2, and this is show that the functions e raised to x, e raised to 2x, e raised to 3x are linearly independent. Let c1 e raised to x plus c2 e raised to 2x plus c3 e raised to 3x is equal to 0. Therefore, c1 e raised to x divide. Therefore, c1 plus c2 e raised to x plus c3 e raised to 2x is equal to 0. Differentiating about two equations, therefore c2 plus 2c3 e raised to x is equal to 0, and so on and so on.